This movie is for Learning Target 2, Geometry, Similar Polygons. Let's look at the warm-up. A movie theater screen is in the shape of a rectangle 45 feet wide by 25 feet high. Which of the TV screen's formats at the right, standard or letterbox, do you think would show the most complete screen from a movie shown on the theater screen? Explain. So let's look at this ratio, 45 feet wide to 25 feet high. You can see that the standard and the letterbox are also in a ratio, 36 wide, 27 high, and 36 wide, 20 high. If we take those ratios and we reduce them, you see that we get, on the movie screen, 45 over 25 reduces to 9/5. In the standard screen, it reduces to 4/3, and in our letterbox, we get 9/5. So you can clearly see that the letterbox screen has the same ratio as width to height, so that would be the better screen to show it on. Similar figures have the same shape, but not necessarily the same size. So you can abbreviate similar using this symbol. The symbol is very similar, pardon the pun, to the congruent symbol with no equals underneath. Our essential understanding is you can use ratios and proportions to decide whether two polygons are similar and define unknown lengths of similar figures. Adding to our purple sheets, similar polygons. Two polygons are similar if corresponding angles are congruent and the lengths of the corresponding sides are proportional. So notice sides are not congruent, but we're looking at angles being congruent, sides being proportional. So we can see here polygon ABCD is similar to GHIJ. Pause the movie, add this to your purple sheet, press play when you're finished. You can write similarity statements using corresponding vertices in order just as you write a congruent statement. When three or more ratios are equal, you can write what we call an extended proportion. So it's not just two fractions equal to each other, you could have 3 or 4, and that's called an extended proportion. We have a scale factor, which is the ratio of the corresponding linear measurements of two similar figures. The ratio of the lengths of the corresponding sides BC and X and YZ are more simply stated the ratio of the corresponding sides. BC is to YZ, 20 is to 8, and that's the same as 5 is to 2. So the scale factor we say for the two triangles is 5/2 or 5/2. It's the reduced factor, scale factor. Let's look at this with these two triangles. What are the pairs of congruent angles? So we're going to match up the congruent angles. You can do so with the visual or just look here. M is the first one stated, so is S. So we know M and S are congruent, N and R are congruent, and P and T are congruent. Now notice, because we're talking about similar polygons, we're going to write the extended proportion for the ratios of the corresponding sides. So I have MN is to SR as NP is to RT NP as MP is to ST. You can use the visual or you could use the similarity statement here. Take this situation, DEFG similar to HJKL, and find what are the pairs of congruent angles, and also what is the extended proportion for the ratio of the lengths of corresponding sides. Please answer at the end of the movie. Oh, sorry. So that means you can go ahead and try this now, but you'll answer it at the end of the movie. Determining similarity. Are these two polygons similar? If they are, write a similarity statement and give the scale factor. So let's look at these two. First, we want to identify pairs of congruent angles. So we're going to look at J is congruent to T, K is congruent to U, LV, and MW. Then we want to see if our sides are proportional. Do they have the same scale factor? So when we set them up, we see JK 12 is to 6. That reduces to 2 over 1 here. KL is to UV, that is 3 halves. Already we can see these are not the same. LM to VW, 12 to 7. And then this is 1. 6 is to 6. Since corresponding sides are not proportional, these polygons are not similar, even though the angles are congruent. You have to meet both conditions. Let's look at these two triangles. Let's identify the pairs of congruent angles. So we have A is congruent to D, B congruent to E, and C congruent to F. Let's compare the ratios of corresponding sides. So we've got 8 and 10, which is 4 to 5. We've got 16 to 20, which is 4 to 5. And 12 to 15, which is 4 to 5. Even if you did that in the reverse, 5 over 4, you would get that it has the same scale factor. So triangle ABC is similar to triangle DEF, and the scale factor is 4 to 5. Are the polygons similar? If they are, write a similarity statement and give the scale factor. I want you to pause the movie, try this, and press play when you are finished. Okay, so you tried this guy. What I would like you to look at is in A, these are not similar. 10 is 2 times 10 is 20, but 2 times 15 is not 15. It would be 30. So for A, it's not similar. Here we've got our angles, showing angles congruent. And then if I take 9 times 2, I get 18. So these three are corresponding parts are similar. And then 6 times 2 give me 12. So my scale factor is 2 to 1 or 1 to 2. And these two polygons are in fact similar. You can see the similarity statement here. Using similar polygons, we have that they are both similar. What is the value of x? So if I'm trying to solve for x, I know that I can set this up as x is to 7.5, but I have a variable y here. So you don't want to use EF, you want to use what you know. So let's use DE is to DA. So when we set this up, we've got corresponding parts and we're going to use what we know. X is to 7.5 as 6 is to 9. And we're going to cross multiply and solve. And we get x is 5. So the answer is B. We're going to use this diagram, and I want you to solve for y now. And then you're going to put your answer in at the end of this movie. Okay, once you're finished with that, let's use similarity. Your class is making a rectangular poster for a rally. The poster's design is 6 inches high by 10 inches wide. The space allowed for the poster is 4 feet high by 8 feet wide. What are the dimensions of the largest poster that will fit in the space? The first thing you need to do is determine whether the height or the width will fit in the space first. So the very first thing is you've got to get them both into the same units. So you convert 4 feet to inches and 8 feet into inches. There's 12 inches in a foot, so you're multiplying by 12. Then if I take this what's in inches for the height and I divide it by 6, because that's how high the poster is, I see that I can get 8 times. So if I took my poster times 8, it would fit at least for the height. For the width, if I took 96 inches and I divide it by 10, because that was my width, I get that I could get 9.6 times the size. So if I use 9.6, then the height wouldn't fit. And if I used 8, there would be extra space for the width. So you always think conservatively. The design can be at most 8 times because the width will still fit. If I use the 9.6, the height would go over. So the greatest height is going to be 48 inches because I've already solved that. 48 by 6 is 8. So now we need to find the width. So 6 is to 48 as 10 is to x. We can set up our corresponding sides of the similar polygons. We know they're proportional. And we get x is 80. Now 80 is in inches, so we're going to change that back into feet. And so we get the largest poster is 48 inches by 80 inches, or what we say 4 feet by 6 2/3 foot, or you could change that even into feet and inches, which I prefer. I'm going to show you this with another problem as well. If we look at this example, Jan uses an overhead projector to enlarge a picture 5 inches high, 7 inches wide, and she projects the picture onto a blackboard that's 4 feet 2 inches high and 12 inches wide. What are the dimensions of the largest picture that can be projected on the blackboard? So another way to look at this is to first convert both to inches. So the 12 feet is really 144 inches. So I'm going to put that up here. And the 4 feet 2 inches is really 50 inches. Now that they're both in inches, we can see how much you can increase the width. So the width here is 7 inches, and I'm going to see how many times it goes into the 144. It goes in 20.57 times. Let's see how much we can increase the height. So I've got 5 inches here. I'm going to see how many times it goes into this 4 feet 2 inches or 50 inches. So 50 divided by 5 is 10. So we see here that I could increase it 20.57 times for the width, and the height I could only increase by 10 times in order for it to still fit. So you've got to take the smallest amount. You've got to take the 10. Otherwise, the height would be off of the screen. So you use the smaller number since you have to have your picture be on the screen, so we're going to use the 10. Since we're using the 10, we already know the height. The height will be 50 inches. Converting that back, we get 4 feet 2 inches. Now let's find the new width. The width is going to be my 7 inches, which is my original, times 10, which is 70 inches. Converting that to feet and inches, that becomes 5 feet 10 inches. So our answer is 4 feet 2 inches by 5 feet 10 inches. I want you to take this idea and apply it to this situation that you'll answer at the end of the movie. Your class is making a rectangular poster for a rally. The poster's design is 6 inches high by 10 inches wide. This is what you had seen before. The space allowed for the poster is, I'm going to switch that. What are the dimensions? So we're going to use this same idea for the poster. And I want to see if it fits in a space 3 feet high by 4 feet wide. So I want to see what the dimensions of the largest complete poster could be. Pause this movie, try this, you'll answer at the end of the movie. In a scale drawing, all lengths are proportional to their corresponding actual lengths. The scale is the ratio that compares each length in the scale drawing to the actual length. The lengths used in a scale can be different units. And a scale can be in different units. For example, a scale might be written as 1 centimeter to 50 kilometers, 1 inches for every 100 miles, or 1 inch for every 10 feet. You can use proportions to find the actual dimensions represented in a scale drawing. Let's look at this example. Scale factors, just a review from maybe 7th grade. They can be different units, and you relate always drawing to the actual. I think of this as drawing to actual. So scale factor is always DA, drawing over actual. If we look at this design, the diagram shows a scale drawing of the Golden Gate Bridge in San Francisco. The distance between the two towers is the main span. What is the actual length of the main span of the bridge? Here's our scale, 1 centimeter for every 200 meters. Notice that's drawing to actual. 1 centimeter of the drawing is 200 meters actual. So the length of the span in the scale drawing is 6.4 centimeters. Let S represent the main span of the bridge. We're going to use this scale to set up a proportion. So I have 1 over 200 is equal to 6.4 over S, the actual. Again, drawing to actual, we use cross products and we solve. The S is 1280. So the actual length of the main span of the bridge is 1,280 meters. Take architecture. You want to make a scale drawing of the New York City Empire State Building. New York City's Empire State Building using the scale 1 inch for every 250 feet. If the building is 1,250 feet tall, how should you make the building in your scale drawing? I want you to pause this movie, try it, and you'll answer this at the end of the movie. That is the end of this movie for Learning Target 2.